Hello everyone. My name is Ajit Nikat. I am the third year of student of Savitribai Phule Pune University. I have successfully completed my internship at the Emertech Information of Technologies, where I gain a practical knowledge in embedded systems. During my internship, I work on a real-time project, which helped me to understand the both hardware and software integration. Today I am going to present my internship project, explain its working components, use, and applications along with my partner Sarvesh Patak. So now I am sharing my internship learning journey. Our internship at the Emertech provided a comprehensive foundation in embedded systems, from the fundamental programming concepts to the advanced microcontroller applications. This journey equipped us with the essential skills for the real world projects. So this journey is divided into four modules. Every first module is the C programming fundamentals. In this module, we learn about what is a C language, its data types, why it is required for the embedded system, conditional statements, operators, arrays, internal concepts of the pointers, functions, stack, storage classes, and preprocessors. Second module of this internship is the embedded systems and microcontrollers. In this module, we learn about the what is the embedded system, that is the introduction of the embedded system, microprocessor versus microcontrollers, why we need to study the embedded systems, what is its use case. The third phase is the development tool and interfacing. In this week, what we have done, that we learn about what is a MPLab IDE, what is a PiximLab and X8 compiler, what is the need of compiler. And in this section, we also learn about the what is a CLCD introduction and interfacing. In last part, we join the Disha workshop. So presentation roadmap is as follows. This presentation will guide you through the core concepts of the embedded systems and our practical application in simulating a microwave oven. So introduction to the embedded systems, defining what the embedded systems are and their significance. Second point is the microprocessors versus microcontrollers, understanding the key difference between both of them. Third part is the microwave oven as an embedded system, analyzing its embedded nature and functionalities. Fourth point is project requirements, outlining the technical specification required to do this project. Architecture overview, exploring PiximLab and Pix16F internals. Project demonstration, a live showcasing of our microwave oven simulation. Learning outcomes will be reflecting on the knowledge and skills gained. What is an embedded system? So, an embedded system is a specialized computer system. It is the nothing but it is the combination of hardware and software performing a dedicated function within a larger mechanical or electronic system. It operates in isolation, focusing on a specific tasks with a precision and efficiency. An embedded system is an isolated system specially designed to perform a designated function with the help of its hardware and embedded software. These systems are ubiquitous, found in everything from household appliances to the complex industrial machinery, making our world smarter and more responsive. So, anatomy of an embedded system is as follows. The structure of an embedded system is a tightly integrated network of components working in harmony to achieve its designated function. Sensor, ADC, that is the analog to digital converter, processor, DAC, that is the digital to analog converter. At its core, a basic embedded system comprises sensors. Sensors convert the real world physical data like temperature, pressure into the electrical signals. Analog to digital converters, that is a ADC, transform these analog electrical signals into the digital data which the processor can understand. Processors, what is the processor mainly? It is the brain of the system, processing the digital signals and temporarily storing them in the memory for the rapid access. It does not process the analog signals. Mainly, it is a processing the digital signals. Memory. We all know that memory stores both the embedded software instructions and the data being processed. Digital to analog converter. What is the mainly digital to analog converter will do? It converts the processed digital data back into the analog signals for controlling the physical components. Actuators are the execute the physical actions, comparing the actual output against the desired memory stored output to ensure the correct operation. Classifying the embedded systems. Embedded systems are categorized based on their performance and functional requirements, as well as the capabilities of their microcontrollers. This classification helps us to understanding their diverse applications and design considerations. Real-time systems, strict timing constraints critical for applications like aerospace control or medical devices, standalone systems, network systems, mobile systems. These are the some classification of the embedded systems. So now we study, uh, we learn microprocessors and microcontrollers in the internship. So understanding the fundamental differences between the microprocessors and microcontrollers is the crucial for the designing the efficient embedded systems. Microprocessor is a use in a complex computer systems. Microcontroller is a widely used in dedicated embedded systems. Example, various appliances. Microprocessor consists only of a central processing unit CPU, but a microcontroller integrates CPU, fixed RAM, ROM, and other peripherals on the single chip. Microprocessor requires external components, that is a RAM, ROM, input output ports, leading to the larger, more complex circuits will be there. But in microcontroller, all components are internal, resulting in the smaller in size, more compact circuit sizes. Microprocessor in higher power consumption due to the external component interaction. But in a microcontroller, power consumption is less, ideal for battery powered devices. In microprocessor, limited internal register storage. But in microcontroller, abundant internal registers lead to the faster processing and reduce the reliance on the external memory. Next, the microwave oven and embedded system. This is our main project of this internship. The microwave oven, a common household appliance, perfectly exemplify an embedded system. It is an electric oven that efficiently heats and cooks food by exposing it to the electromagnetic radiation in the microwave frequency range. The microwave oven is an household appliance that has revolutionized modern home kitchens. Its speed, efficiency, from its ability to directly channel heat energy to the food molecules. This is managed by the internal microcontroller. That is the main purpose of microcontroller inside the microwave oven, which handles user input, cooking modes, and precise the timing, ensuring consistent results. Microwave oven modes. There are different types of modes in which microwave oven is operating. Our simulation focuses on the key operational modes found in a typical microwave oven, demonstrating versatility and control. Micro mode. Traditional cooking with the maximum 900 watt power and up to 60 minutes cooking time. Grill mode. It is utilizes a dedicated grill heater for grilling effects. Convection mode. Heater and fan circulate hot air for uniform baking effects. Start mode. What this mode is? Initiates the selected cooking process. Project development ecosystem. To successfully implement the microwave oven simulation, we leverage a specific set of tools and software hardware components. Embedded C expertise. Proficiency in embedded C is the fundamental for programming the microcontroller's logic. MPLAB IDE and XC8 compiler. The integrated development environment IDE and compiler for writing, debugging, and compiling the code. PixSimLab simulator, a crucial simulation tool for testing and verifying the code without physical hardware. We don't require any hardware for this project. PIC16F microcontroller, the core processing unit for our simulation. It is a very core processing unit for our simulation. that is a PIC16F microcontroller acting as the microwave oven's brain. Key peripherals: 16 by 4 CLCD for displaying information to the user, tactile switch for basic user input and control, MKP, that is a matrix keypad for detailed input such as a setting, time and power, timers. Timers are also very essential for precise control of cooking durations and processes. Unlocking the power of embedded C. Welcome to the world of embedded C. This presentation will guide you through the essentials of programming microcontrollers, bridging the gap between hardware and software. We will explore the tools, architectures, and concepts crucial for any aspiring embedded systems engineer. Embedded C versus Standard C, a core distinction. Standard C programming, it is the native development environment, hardware independent and versatile. Mainly, it is a used for desktop applications, operating systems, and general purpose computing. Embedded C programming, it is a cross development in nature. It is a mainly hardware dependent, exactly opposite to the standard C programming. And it is optimized for limited resources, that is a RAM, ROM, and input output peripherals. While both use the C language, embedded C incorporates specific extensions to interact directly with the hardware components, making it ideal for specialized applications. MPLAB IDE, what is this mainly? V5.35 is the version, your development hub. MPLAB IDE, developed by Microchip Technology, is a powerful integrated development environment designed for microchip microcontrollers and digital signal controllers. It streamlines the entire development process from writing code to the debugging. Key features: project creation and efficient management, robust debugging and simulation support, seamless build and compilation using X8 compiler, comprehensive device configuration and programming tools. PixSimLab. What is this PixSimLab? It is the bridging simulation and reality. Now we are discussing about the PixSimLab. PixSimLab is the real-time emulator. It is an emulator that brings our embedded designs to the life virtually. No need of hardware. It supports the various devices and offers integrated debugging with the MPLAB. PIC16F microcontroller interfaces. It is a GPIO for general purpose input output, I2C for communication with the RTC and EEPROM, LM35 temperature sensor for analog input, ADC for the analog to the digital conversion, output and interface devices in PixSimLab. RS232 standard serial communication, mainly it is used for standard serial communication. LEDs is a visual indicators, we all know that. Buzzer is for audible feedback. Digital keypad, it is a mainly for user input interface. 7 segment displays for numeric output SSDs. Matrix keypad to give the advanced user input. CLCD is the character liquid crystal display. These devices enable the comprehensive simulation and interaction with embedded projects. PIC16F microcontroller, the workhorse. The PIC16F is a popular 8-bit microcontroller from Microchip Technology, widely used in various embedded system applications due to its robust feature set and versatility. It is the 40-pin DIP package, easy for prototyping. It is a 8-bit RISC architecture for efficient processing. 14 kilobyte flash program memory for code storage. 368 bytes RAM and 256 bytes EEPROM for data. 33 input-output pins across the 5 ports, that is port A to port E. Integrated timers, that is a timer 0, 1 and 2. Built-in ADC module for analog inputs. Supports the USART, SPI and I2C communication. These are the some types of communication. This is the architecture of PIC16F877A microcontroller. So we know that there are 5 ports and 3 timers are there. USART communication is followed by this microcontroller. The PIC16F employs a Harvard architecture. This PIC microcontroller follows the Harvard architecture, distinguishing between the program memory and data memory. This separation allows for simultaneous instruction fetching and data access, enhancing the processing speed and efficiency. Tactile switches it enabling the user interaction. Tactile switches are fundamental input devices in embedded systems, providing a distinct physical feedback when it is a press. It is a normal like a switches. They are critical for user interfaces in many applications, from simple appliances to the complex control panels. Versatile selection. It is available in various sizes and mounting options, allowing customization for diverse applications. Project application. It is a use to select the modes of operation and set parameters like temperature and time in this project. Understanding the bouncing effect. It is a common phenomena where spurious pulses are detected during the switch activation or deactivation, requiring debounce techniques in software. Matrix keypads, compact input solutions. Matrix keypads offer a compact and efficient way to accept a multiple user inputs while minimizing the number of microcontroller pins required. This makes them ideal for devices with the limited input output. Row and column arrangement, optimized pin uses, and common applications it found in everyday devices like microwave ovens, gas pumps, and calculators. Now we are discussing about the interrupts and timers. Interrupts. An interrupt is a crucial mechanism that allow a device to signal the CPU to the monetarily halt its current task and execute a specific piece of code in response to an event. So timers are essential for precise timing and sequencing of events in embedded systems, ensuring operations are synchronized with either system or external clocks. Interrupts are the event-driven processing, enables the external and internal devices to request the immediate attention from the microprocessor or microcontroller. But timers, accurate time delays, used to generate the precise time intervals crucial for scheduling tasks and controlling durations. Second point for the interrupt is it is an interrupt service routine ISR, a dedicated software routine that processes the interrupt and then gracefully returns control to the main program, ensuring timely responses to the critical events like keyboard presses. Second point for the timer is PIC 16F timer modules. Features 3 timers, 2 8-bit that is the timer 0 and timer 2, and one 16-bit that is the timer 1, supporting the various timings, counting, and PWM generation operations. Microwave oven simulation, MPLab IDE, and PiximLab. This project demonstrates a comprehensive microwave oven simulation leveraging the power of the PIC 16F microcontroller within the integrated development environment of MPLab IDE and the realistic simulation capabilities of PiximLab software. It eliminates the need for physical hardware, providing a complete virtual prototyping solution for the embedded systems development. It is a totally virtually prototype solution.
Hello everyone, my name is Sarvesh Sanjay Pathak. I am third year student of SCOE college. Here I have successfully completed my internship in Emertxe, and now we are in MPLabX IDE. In micro one there are 5 files: header file, important files, linker file, source files, libraries, and loadables. In header files there are 4 subfiles: CLCDH, matrix keypad h, micro one, and timer.h. In source files there are 6 subfiles: clcd.c, isr.c, main.c, matrix keypad.c, micro1.c, and timer.c. Now we have to build this. For this I press build project micro1 and build successful. Now we will use PiximLab, in which there are 4 modes. So to start my demonstration I need to configure few things. The board which I will use is big genius, and the microcontroller is PIC-SIM 16F8 double 7 digit. We can see the micro grill, convection and start mode on it. There are 4 modes. Before this message was displayed powering on and microwave. Now I will be giving a demonstration of my project. So before that, as once earlier, as I have explained, microwave oven is an electric oven that heats and cooks food by exposing it to electromagnetic field radiation in the microwave frequency range. In this busy life, microwave oven are useful for cooking purpose. So after the configurations, I will now start the project demonstration. So I have told about the configurations. The LCD here is of two types, 16 cross 2 and 16 cross 4. Here I have used 16 cross 4 LCD. So there are 4 modes in my project: micro mode, grill mode, convection mode, start mode. In order to implement micro, I we need to press 1. To implement grill mode, we have to press 2. For convection mode, press 3. And to start mode, we have to press 4. So let us start with micro mode. So I will be pressing here 1. So the maximum power set is 90 volt, 90 watt. So the time format is 1 minute, minutes and second. So I will setting time for 1 minute, 1 minute 22 seconds. In order to erase this value, I have to press start key. So this clears the entered value and displays 00 value. Now I will be giving new value as 40 seconds. So in order to enter this, I have to press hash key. So now we can see my timer has started and fan has started to rotate. In order to resume this time we need to press 4. To pause 5, and to stop we need to press 6. I will be pausing my timer now. As we can see, I have paused my time at 22 seconds and fan has stopped rotating. So to remove the timer I need to press 4. So now we can see I have resumed my time and fan has started to rotate and the buzzer should be on. The left side here the buzzer sound is heard and cooking time is up message displayed to the green screen. Now we are done with micro mode. Moving on the grill mode. For implementing grill mode, we need to press 2. So just like micro mode, we need to give some time. Here I will be give 44 seconds and hash key to enter the same, like 4, 5, 6, 4 to resume, 5 to pause and 6 to stop. If I press 4 without pausing, my the timer will be implemented by 30 seconds. So I will press 4 and now we can see the timer is implemented to 30 seconds and so on. And the last two modes are there, which are convection and start mode. The working of convection and start mode is same as micro and grill mode. So this is my project microwave oven simulation. And in conclusion, bringing and theory practice. This microwave oven simulation project stands as an excellent example of how modern development tools can bridge the gap between theoretical knowledge and practical applications in embedded systems. By utilizing MPLabX IDE and PixSimLab, students can confidently explore, design, and validate complex systems. Thank you.